I'm not going to use the word stupid, but it's confusing, right? So, what did we talk about last time? We talked about 200 years ago, some fellows in the United Kingdom, one of them was Scottish, two of them are British, and they figured out how to do something very important. What was that? Yeah.
Basically make a steam engine.
Yeah, so they figured out that if you burned fossil fuel, in their case it was coal, because that's what they had, you would produce heat. And that if you took that heat and boiled water in a boiler under pressure, you would produce steam. That was no big news. But then Newcomen figured out how to create an engine that used that steam to drive a piston back and forth, and now you had an engine that could do work. Okay? Just like your car engine. Instead of steam, it uses vaporized gasoline that is sparked and blows the piston back and forth. The original engine was steam. Okay? And then you could then pump water, you could have looms and things like that were powered by this mechanical force. So now you've created machines that do work much faster than people could. And that was the beginning of what was called the Industrial Revolution, because it was such a radical change. Okay? We're living in the time that historians have already called the Digital Revolution, okay? Where things are changing so rapidly and so permanently because of the combination of computers and information systems in the digital world. And that's now the digital revolution. That's what you're living through. But that was a big thing. And why is it important for climate change? What does it have to do with climate change? Or with climate, or all kinds of things? You're studying for the test.
It's more CO2 and
Yeah. So to produce the heat, to drive the machines, you had to burn carbon of some form. We'll talk more about that later. And that releases carbon dioxide. So carbon dioxide that normally would not have been released, had never been released, suddenly started being put into the atmosphere. That was the beginning of it, and it's been going on ever since, at an ever-increasing rate. Okay? So this is when the experiment started. A whole bunch of things happened as a result of the Industrial Revolution, but this is one of them, right? And it was about turn of the 19th century, about 1800. Okay? Let's take a look. So, this is how we ended last time. And notice we've, out of respect, they've named the units of energy after two of these dudes, okay? So James Prescott Joule, who was a physicist, did a lot of work in energy and understanding of how energy is transferred, etc., laws of energy that cannot be broken. And then there was an engineer, James Watt, and those two guys put together a lot of knowledge that they added to about what's called thermodynamics. And then Newcomen, who was a self-taught inventor, okay, figured out how to make a steam engine and actually make a steam engine that worked, all right? And that was the beginning of the world of machines, okay? Of course, they got a lot more sophisticated than a steam engine. But that was the initial trains until well into the 20th century. The trains that ran around the world were steam engines. They burned coal. Okay? But burning coal adds CO2. Okay? Burning oil adds CO2. Burning natural gas adds CO2. Okay? Any form of carbon, which is our main fuel today, is going to add CO2 to the atmosphere. It's a byproduct. At the time, they didn't think anything of it. Big deal. Okay? So this is where we're at, a little over 400. And remember, it's important to see these wiggles that the CO2 goes up and down with the seasons. So photosynthesis, during our summer, it draws the CO2 down a little bit. And then during the winter, when all the plants have gone to sleep, the CO2 goes up. So it goes up and down, but the trend is very clear that it's accelerating upward. Accelerate means it's not increasing at the same rate. It's going faster. Okay? The slope of the line is getting steeper and steeper and steeper. Why is that? Because the rate that we're putting the CO2 into the atmosphere is going up. Why do you think that's going up? There's really two reasons. More people, and more burning of fossil fuels to produce energy, because the average person on the planet is using more energy than they did 10 years ago. You have countries that are developing, and as they're developing, they're using more energy. Okay? So those two things combined means that the rate of CO2 being put in the atmosphere is going up substantially. And compared to 1800, where really only a tiny amount was going in. Okay? Yes?
Would deforestation have anything to do with it as well?
Yeah, we're going to talk about that. That's a great question. So we're going to talk about that later. Since plants absorb CO2, okay, and then that carbon is in their structure. Okay, so a tree is a lot of carbon. Well, if you cut the trees down, you do two things. One, it's no longer pulling carbon from the air. And two, when it decays, it releases the carbon that was in it. So deforestation does have an effect. It's much smaller than the burning of fossil fuels, but we'll see it does have a significant effect. We don't just measure CO2 at Mauna Loa anymore. We measure it at various other places, and everything's showing the same. Okay? So we have multiple measurements. Mauna Loa is just the oldest. Okay? And that's since 1958, and that's the best direct measurement. But we have indirect measurements. We'll talk more detail about how these were obtained. They're from ice cores. Okay? But the point is that it says for centuries, it's really for hundreds of thousands of years, actually for millions of years, the highest CO2 concentration had never been above that line. Okay? And here we are now, way above the line. And look how fast we went up. Because we started here at the end of the last ice age. And actually until about 150 years ago, we were still wandering around here. And then, okay? So we're in unprecedented territory. And we'll talk more about it, but where we're going is uncertain. But where we're going is certainly going to be way above any level that's ever existed in the past. Okay? whether it's 550 or whether it's 1,000, okay? It's all new. It's significantly higher than it's ever been, and therefore it's an experiment, okay? It's an experiment. However, the good news is we're still at the point where we could have a big effect on where we end up, okay? So in other words, there's a big difference between 550 and 1,000. And we have the ability, it seems, to decide and affect whether we end up at 550 or 1,000. That's a huge difference, okay? So there's still a huge opportunity to affect the future. However, we're not going to end up here or here or here. We're going to over 500. That's going to happen, okay? But the question is, do we follow the green line or do we follow the red dotted line? That remains to be seen. Okay? So there's good news and bad news on this. Bad news is we're headed to unprecedented territory. Good news is we can have a huge effect on how far up we go. So again, it's the greenhouse effect. Right now, this arrow is bigger than the sum of those 4 arrows. Okay? These red arrows are losses. It's infrared energy that's leaving the Earth. It's gone. And this arrow represents the radiation received from the sun. Okay? If we were in equilibrium, or in other words, if we were not doing anything in, say, up until about 1800, on average, the size of this arrow and the size of all those arrows was the same. So the temperature was more or less constant. But now, they're not the same. There's a small but significant difference in energy received and energy lost, and it's because of the greenhouse effect. Okay? Because of that. Because of this. These 2 arrows. These 2 arrows have gotten bigger, which means the arrow at the top has gotten smaller. Okay? We're not changing the sun. The sun's still doing what it normally does. What we're doing is we're reducing the loss by adding something in here that's returning some of that infrared radiation. That's the greenhouse effect. Yes?
So, do the greenhouse gases like CO2 affect like how much radiation the sun puts in?
No.
Makes sense.
Some gases affect how much radiation reaches the surface from the sun, but the greenhouse gases don't. So the sun is, the amount of radiation we're receiving from the sun has not changed. Okay? It's only the infrared part of it that's changed. The radiation emitted by the Earth, that's what's being affected. Okay? And we'll see later, they've looked at the sun, looked at it from every direction possible. We have good measurements. It's not changing. Okay? It's warmer now, and it's not because of the sun, which would be the first suspect. It's not there. Okay? So, we're going to go back and deal with carbon in more detail later. But now I want to start a short discussion on basically 2 sections of the globe and a very quick overview of how does the climate system work now, okay, in a very shallow way. If we want to understand how something that's happening is changing the climate system, then we better have a little bit of an idea of how it works now. How does it normally work? Otherwise, it's hard to understand how you're changing it if you don't know how it works to start with. Does that make sense? So we're going to get a very brief introduction into how the climate on Earth operates, and it's different in different parts of the Earth. So we're going to deal with the tropics today, And then later, we're gonna talk about the mid and high latitudes where we live, because the way the climate system works here is very different than the way it works in the tropics. All right? So let's start a little with the tropics. Remember,